about in terms of parallel lines, and we're going to drop into some new skills related to triangles as well, but the first two are a little bit reviewish, which is a great way to start. So what I want to do for our minds on is to review some of the key things you may have learned before. So if we have two lines that intersect like this, we know that there is a relationship between the angles here and here, and also the angles here and here. And what we know is that the two blue circles are equal to each other in size, and the red X's are also equal to each other in size. And these are called opposite angles, and they are always the result when two lines cross each other. Another relationship that we already know about is that if we have a straight line, something like maybe like an x-axis, although it doesn't have to be orientated as such, and if we have another line go up like this, we know that there is a relationship between the red x angle and the blue x angle. And that relationship is the fact that the x and the blue dots, when added together, are equal to 180 degrees. And we call these supplementary angles. So as long as you know the value of one of them, you can easily find the other. A similar relationship exists between two angles that are the result of cutting a corner into two pieces, and they don't have to be identical in size. They could be. They would both be 45s in that case. But we also know that angle X plus blue circle are equal to 90 degrees. And these are called complementary angles. All right, so some simple angle relationships not relating to parallel lines. Now, let's go to a situation where we've got some relationships within sets of train tracks or parallel lines. The first one we want to look at is where we have a set of parallel lines and they have a line crossed through them, which is called a transversal. And there's a number of cool patterns that we can see when a transversal crosses two parallel lines. The first one is, we notice if we look inside the parallel lines, that this angle here and this angle here are both less than 90. Not only are they both less than 90, they're actually identical. And the same thing can be said for these blue angles too. So this is an example of something called alternate angles. Or you may have remembered an acronym called Z. And the reason that that acronym helps you to remember them is that if you create a letter Z such that you go along one of the parallel lines, down the transversal, and out the other side along the second parallel line, you see the letter Z, and you notice that those red dots are at the same position inside the letter Z. Now you're not limited to creating a Z in one direction only. You could also create it in the other direction. So you could have a Z that goes backwards, if you will, across here and down and back out. And you would notice that the blue X's are in the same location along that Z in terms of both being greater than 90 as well. And so sometimes you have to look for that letter Z in a couple of different orientations, but you can identify angles that are the same or that are alternate by looking for that pattern. Another pattern you can look for in a set of parallel lines, if you have a transversal, is to look for angles that are both. And what I mean by that is that they have to both be above or below the parallel lines, and they both have to be on the left or the right of the transversal. So let me show you what I mean. Let's pick this angle right here. And we notice that this angle is below the parallel line and to the left of the transversal. So if I look for another angle that is below the parallel line down here and to the left of the transversal as well, In other words, these are both below the parallel lines and both to the left of the transversal. These are called corresponding angles. And sometimes the letter F can help you remember how to identify those. If you want to see what I mean, this would be a backwards F in this case, where the horizontal lines in the letter F fall along the parallel lines and the transversal makes like the upright part of the F. And you can see that they are both below the horizontal lines of the F and both to the left of the letter F. So you can find all kinds of cool corresponding angles this way. You can also identify that the ones that are both above and both to the left must be corresponding angles. You can also identify that these ones right here are both above but both to the right of the transversal. And in a similar fashion, you notice that these two angles that are here, both below the parallel lines and both to the right of the transversal, would also be corresponding angles. So there's all kinds of them in there to choose from. A third pattern that exists in parallel lines where a transversal is present is a little bit different. These are called co-interior angles. And the letter C is useful in helping to identify them. Now, because they're both co-interior, that means that they are inside or between the parallel lines. So an example of co-interior angles might be here, where these are both to the same side of the transversal, in other words, they're both on the right, and they're both inside the train tracks of the parallel lines. What's a little bit different in this rule is that co-interior angles, of course, add up to 180 degrees, which is different from the first two patterns where there's no addition relationship present. Okay, so we've got alternate angles that form a Z, corresponding angles that form an F, and co-interior angles that form a letter C. And again, it doesn't have to be a C the way we read it. We could also have a C going backwards over here as well with a set of co-interior angles too. All right, so there's a little bit of background in terms of some angle relationships that you may have seen before. Next, what we want to do is clarify for you the difference between two new terms, congruent and similar. So I like to think of congruent figures as being twins. Twins in every possible way, or clones of each other. So an example of congruent shapes would be, for example, my square sticky note. And if I wanted to have a congruent square, it has to be an identical sticky note. Now, they don't necessarily have to be orientated the same. One could be turned sideways, one could be straight across. You know, I'm not adjusting the size or the shape of this square. No matter how I turn it, they're still congruent. Okay? What I like to do is compare that to things that are similar. So similar might be like siblings. You could say to them, oh, you can tell that you're siblings, but they are not identical, not like twins. So similar would be, for example, a square that is this size, a little mini-me or a mama bear square. We have Papa Bear, Mama Bear, and Baby Bear square. Now the reason that they're similar is because they have the same shape, they're all squares, but they're proportional. So one is a smaller version of the next. I like to call them mini-me's to help you remember the difference. Okay? So our focus in this unit is going to be on properties of similar shapes, most specifically similar triangles. Congruent is easy to remember because it's just the same shape, cloned or repeated. All right, so moving along the idea of similar triangles, let's review a little bit about some triangle notation that you may have learned in times past as well. So if we have a triangle that looks like this, there are a lot of things we'd like to be able to refer to in that triangle, specifically sides and corners. So often we will label the corners of a shape using capital letters. Sometimes we can go around clockwise, counterclockwise, it really doesn't matter. I'm going to label this one ABC. And so if I call this triangle ABC, that's the same as calling it BAC, CBA. Doesn't matter what order those go in, but I usually try to give the listener, the person I'm communicating to, an idea of the order of them. If it has more than 3 points, the order would matter. But triangles, doesn't matter what order you say them in, you're going to be able to visualize that triangle. Now, I also might be interested in this point at some point, and I'm going to call it D, something different. When I refer to the sides of a triangle, I could call this side a couple of different names. I could just simply call it AB because it connects vertices A and B, but I could also call it by the letter that is opposite its angle. I could call it little c, and we'll come back to that notation a little later in the unit. For now, we will use the capital letter notation for the first couple of lessons. Okay. In a similar fashion, I could call this side AC, or because it's across from angle B, I could also call it little b. And then similarly, I could call this one BC. If I want to talk about sections of BC, I can refer to this as BD, and I can refer to this as DC or CD. We tend to list them alphabetically when we have pairs of letters, but it doesn't have to be that way either. Okay. The other thing we want to be able to communicate to other people too are specific angles within that shape. So if I want to look at this angle here, I have a couple of different ways I can name it. I could just call it angle B. And I'm going to use a capital letter again for the corners of a shape. Another name it might go by though too is ABC or CBA. I have to make sure that the corner I'm referring to is in the center of this 3-letter notation for referring to a specific angle. If it's at the beginning or the end, then it means it's not where the actual angle is. Okay, so just a little review there on how to label triangles so you can communicate your ideas very, very clearly. All right, now, in today's lesson, what